The electrolyte,
Loading is what, hydrogen or deuterium?
it's hydrogen. The electrolyte is 1 molar lithium sulfate in water.
In water?
You have time for a question, please?
Hey, yes, Dennis, how do you estimate your surface area for your current densities?
The surface area, we've got roughly 1,200 beads in there and 1 millimeter across. I think it comes out to be like 30 square centimeters, something like that, overall. We don't know how far in the beads it's really going.
Shading and what have you and stuff.
What?
Question, have you run this for a long time so that, you know, you're just not getting some initial reactions and whatnot?
They have been run for several days. Realize we only have about 40 milligrams of metal in the system because it's just 2 microns on there. And that means that it's probably ideal type of thing for somebody looking for isotopic shifts of the metal lattice because there's so little metal in there. Over a couple of days, we'll be up in the megawatts, megajoules per mole type range because we have so little palladium in the system.
Sure, but give the excess watts. I mean, it's nice to have it both ways.
Yeah, in watt, our excess watt, we're putting in about a half a watt in and getting out 1.7 watts as we speak right now. So roughly an extra watt. You take a watt times seconds, hours, you know, you can get, and we've got 40 milligrams of metal in there. You can figure out how long we need to run it. But they've been running a week or so.
Last question.
Yeah, two quick questions. It wasn't clear to me whether, are you using heavy water or
It's normal water, 1 molar lithium sulfate.
The other question was, what is the reason for the nickel?
It's a nickel, palladium, nickel. We assume that what's happening materially is when you lay a plate on another, your loading times decrease. You're sandwiching the palladium between the nickels so it's mechanically held, and also because the lattice spacing is different, every 30 or 40 atoms you have to have a dislocation so it can hydride better. So I'd recommend people to look at plating and particularly multiple plating systems because they load so much quicker.
You also could get a preferential face. You could get a particular face instead of plate.
Right.
That might be very important.
Right.
Thank you.
Next paper is by Dr. Deya. Anomalous thermal effects in the P2PD Mallove electrode molten chloride alkaline nuclide systems.
I would like to talk about work which was done in collaboration of ENECO and Institute of High Temperature Electrochemistry in the Russian Academy of Science. This work has more verification orientation rather than just scientific. Because of the nature of ENECO business is intellectual property acquisition, one point of time it's a peer question if molten salt technology, we will call technology, is valuable for further development and review. In this case, the problem was that Dr. Liao, who has, must be credited for first experiments with molten salt, has some problems with replication of his experiments. In this case, ENECO make arrangement with Institute of High Temperature Electrochemistry, who is naturally probably best choice in Russia, to conduct experiments to verify if it's working or not. So for our experiments, we took entirely Dr. Liao published papers and all information which he could supply us about this. It was built electrolytic cell which mostly replicate Dr. Liao experimental setup, and which comprises aluminum cathode and molten salt and palladium anode. The difference in molten system is that reaction is supposed to occur in anode rather than cathode. difference between Dr. Liao's setup and our setup is that he, during experiment, must to add lithium deuteride to system because of evaporation and running out. So in our experiment, this is completely sealed cell. All this small electrolytic cell was placed in quartz tubing and supplied with rubber stopper. During experiment, we pump out air and push with helium, and all reaction, all process was in helium protected atmosphere. Also, difference is that we run not just deuterium, we run comparison experiments. So, two absolutely identical electrolytic cells, but one of them was filled with lithium hydrogen, another with lithium deuteride, were placed in rubber massive block and connected in series. In this case, equal amount of electricity comes through both cells. And thermocouples were placed just above palladium anode, so we can monitor temperature, and it was monitored temperature difference in hydrogen and deuterium cell. All this system was placed again in a quartz vessel and then installed in oven. Temperature difference across oven was no worse than 0.5 centigrade, so it's quite very similar conditions. Again, experiments were exactly like Dr. Liao made, and he ran about 1.5 days loading cycle with low current, about 4 milliamps per square centimeter in anode, and then apply sharp current increase. Also around oven was placed 2 flat neutron detectors. So this is for our first experiment. So what we found? So these curves illustrate not temperature. This is differential temperature between hydrogen cell and deuterium cell. This is quite no difference when current is small and steady, about 4 milliamps per square centimeter, like here. But we have, when we increase current up to 290 milliamps square centimeter, we have very good difference in temperatures. So this is deuterium cell produce heat up more than hydrogen cell, and this kind events happen 4 times. What is really interesting that in this experiment we detect neutron emission strictly correlated to these heat events, and what unfortunately we didn't get in 2 following experiments. And we believe that the reason is that in our first experiment was used lithium deuteride in monocrystallic form, which we get from stock of Institute High Temperature Electrochemistry. And 2 follows experiments were run with lithium deuteride from Aldrich, which we get from Dr. Liao. So this is probably quality of lithium deuteride is critical for this thing. However, in next experiment, we also can see temperature difference exactly in similar conditions between hydrogen and deuterated cell, with some time delay. So we believe that quality of electrochemically active material, lithium deuteride, is responsible for this. So third experiment shows more detail, temperature plot in lithium cell and hydrogen cell, which always below, and difference between these two cells. After these 3 experiments, which quite consistent and successful, we perform experiment with calorimetry. So we've set up in oven. It's very difficult to evaluate heat thermal balance of the system. So next experiment were just single, and we run in they were performed in dual vessel with good insulation. So here we have plots of 3 experiments. Always we observe increase of temperature during sharp increasing of current density. And in our best experiment, we got about 23 centigrades of heating deuterium, deuterated cell versus hydrogen cell. However, we didn't register any neutron emissions anymore. And in our best achievements and heat excess was about 10%. So we didn't get no more than this. So we believe that these experiments now would verify that molten salts, their perspective, and that results which Dr. Liao presented is quite reliable. So I have all to say.
Could you say something about the calorimetry, total energy?
Well, this is microcalorimetry. You know, what is make us very confident about this result? That in this is not a single scientist work. It was teamwork. It was about seven scientists involved, and 2 of them, they're top Russian scientists in microcalorimetry of molten salt system. So power applied to cell was about 0.97 watts. This is really small cell. So and it was heated about 370 centigrades, but this is really small energy level. And heat which we observed was about 0.08 watts, so about 10% approximately.
And for how long?
All time of experiment was, each experiment was running about 3 days constantly. And about 1.5 days we start, when we consider that this is loading period and we accomplish it, we start cycling, current cycling. And it was about half hour, and then effect decreased. This is exactly like in our plot, so this is, this is minutes, 10 minutes, and then it's done.
Did you have a conclusion as to why Liao and Liebert may not have been able to reproduce their initial results?
We visit with Dr. Samgin and Dr. Academician Barboshkin, we visit Dr. Liao's lab in Hawaii, and he performed his experiment in glove box. So he forced to add lithium deuteride during his experiment. So there is number of variation you cannot monitor. So that's why I decided to make sealed cell. So we didn't add any lithium deuteride during the experiment. This is completely sealed system, closed system.
What could you?
Take it that you didn't do this, but I know that Liebert and Liao had their electrodes analyzed afterwards and found significant amounts of residual helium-4.
We didn't make. We were not able to make such kind of tests.
But maybe in the future you might like to try to do that.
Probably, but again, this is not a steady research program. It was experiment for verification. So we believe that we verified it. And what is, for example, we had very big discussion between us, people who involve in experiment with Dr. Liao. For example, what make us very curious? We use very pure materials. We use monocrystal lithium deuteride, but Dr. Liao used melted by acetylene torch anode. So you immediately introduce a bunch of impurities. It make us really curious. But anyway, we did this. So we use pure beryllium oxide cast, and we melt pure palladium tubing to make anode. However, we cannot, guarantee that this is still pure because you use just regular torch. I don't know.
Yeah, could you repeat the difference in the electrolyte between yours and Liao's?
Yes, of course. Dr. Liao used, how we know, he used Aldrich chemical grade lithium deuteride. When we use monocrystallic lithium deuteride, but supply was very, very limited, and it was from Stock Institute of High Temperature Electrochemistry. So monocrystallic is much purer than polycrystallic. This is the purest version you can get, probably.
Yeah. And that's what worked well.
And we believe that this is why. This is a good chance to believe in this. But I cannot tell. Thank you.
So we are going to have two talks from the NHE project, which is now running in Japan. The first one is present status and perspectives of new hydrogen energy project by Dr. Asami from NHE Laboratory in Sapporo.
Thank you very much, Chairman. April is the season of cherry blossom in Japan. So many petals are falling down on the films. I'd like to introduce the outline of NHE project and recent activities conducted in the NHE laboratory. This NHE project has been announced and introduced in past ICCF-5. Many of participants will remember the existence of this project, I think. The purpose of this project are to confirm and demonstrate an excess heat generation phenomena. And second, to make clear the heat generation mechanism, and to make an excess heat generation controllable. And finally, to clarify feasibility of NHE as one of future energy sources. The project has been started in November 1993 as a 4-year national project with total planned budget about 30 million. We have received 2.5 million in 1993 and $5.4 million in 1994. This is the organization structure of national project. Ministry of International Trade and Industries subsidize New Energy and Industrial Technology, NEDO, and NEDO has contracted with Institute of Applied Energy, IAE, to conduct this R&D project. IAE has established R&D Center for New Hydrogen Energy, which is composed of center of office in Tokyo and laboratory in Sapporo. And steering committee, three steering committee was established in NIDO. And first committee is responsible to determine a basic plan and action programs. The second to evaluate R&D results. And third to plan and manage the action programs. NIDO also coordinate and promote international cooperation programs. Research and development programs and items conducted in NHG centers in 4 categories. Demonstration experiments of excess heat, material science programs, establishment of database and feasibility studies, and finally, international cooperation. This is the progress of the project. And 3 NHG steering committees was held in first December 1993 and second May 1994 and third December 1994. And fourth steering committee will be held in this June. In this committee, we present an annual report and to be determined action program in fiscal year 1995. As an important event at the middle point of this project, we make interim report and summarize internal and international progress of this field. And then evaluation of NHG project and the result will be made in this December. The chairman of this intermediate evaluation is Professor Ikega. This figure shows the master program of each item of energy project. We have conducted mainly the item reproducibility of excess heat and characteristics of existing materials and database manufacturing and international cooperation until fiscal year 1994. And as new activities from fiscal year 1995, verification of reaction products and development of materials and new methodology will be emphasized. This one and this one. This figure shows a milestone chart of energy R&D items. In the open type electrolysis cell experiment and fuel cell type electrolysis cell systems, reproduction experiment is conducted until this fiscal year end. And in the open type electrolysis cell, improvement of Icarus 1 to Icarus 2 was completed in this February. And in the flow calorimetry systems, development of our own flow calorimetry systems were conducted in this year. And introduction of SR-type flow calorimetry system from McBride are completed in March. And observation and analysis of palladium electrode and cell components has been conducted continuously as it necessity. And below, I would like to summarize about the recent major activities and results attained in NLG laboratory. In the field cell type electrolysis, measurement of B by PD ratio, excess heat, and absorption and desorption rate, observation of surface and cross-sectional microstructure, and analysis of surface and inner impurities and crystal structure have been conducted using various source palladium. As major results attained in these items, excess heat of 9 to 15% have been observed with high purity palladium in 2 cases. However, the reproducibility issue still remains, and the D by PD loading ratio of 0.89 and H by PD ratio of 0.93 was attained with high purity or single crystallized palladium. And understandings of material characteristics have been advanced. In the plan in fiscal year 1995 to see the essence of material characteristics for higher loading ratio and to increase the reproducibility of heat generation. Introduction of Icarus 1 system from Professor Fleischmann and Professor Pons in early 1994, and started electrolysis of palladium and palladium silver alloy from Johnson Massey with relatively low current density from February 1994. And as a result, need to improve precise calorimetry and to upgrade the cell components and instrumentations. Then, the modifications described below were performed according to the suggestion of Professor Fleischmann and Professor Pons. And now, version up to Icarus 2 system from Icarus 1 to measuring boiling region phenomena completed in this February. As a plan in fiscal year 1995 in open types system, we continued experiment with Icarus 2 system and to reproduce Fleischmann-Pons phenomena with higher current at near boiling point and evaluate the accuracy of measurement and data analysis method. And in the item of material analysis and material development, observation and comparison of various source palladium metals for pre and post electrolysis. And the detail will be present in another oral sessions. And as a result, following have been understood, namely identification of microstructure, various type of defects, impurity, and existence of beta phase. And second, surface defect such as microcrack, pore inclusion caused low loading. And existence of impurities on surface such as lithium, platinum, gases, silicon, aluminum, and etc. were confirmed. And standardized palladium treating process has been proposed, namely 4,9 purity palladium used and vacuum melted annealing in vacuum and remove surface defect and impurities. This process is almost the same one explained by Dr. McHugh in this morning. In fiscal year 1995, we will continue the observation and analysis on selected palladium specimens and perform loading experiment with electrical resistance measurement and carry out pre-electrolysis of lithium OD to remove H2O component and degassing treatment of electrolysis for reduce gases component from electrolyte. And we would like to confirm the reproducibility of high loading and excessive generations. And we have been developed new type, namely MHG type flow calorimetry systems. The major feature of the system are anode material, gas diffusion electrode, the same as Japan type cell. Vacuum sealed heat insulation is used, and outer cooling type and inner cooling type, both type is developed in a cell component. And mass flow meter is continuously measurement, and temperature measurement were made by thermopile and platinum resistance. And in performance of this type of a type of flow calorimetry system is over heat recovery rate over 97%, and fluctuation of flow rate under 0.5%. Plan in the fiscal year 1995, we will start excess heat measurement and confirm excess heat generation in both NHC type flow calorimetry system and SRI type flow calorimetry system. Well, about 40 months have been passed from the start of NHC experimental works. Our R&D effort will be taken more toward fiscal year 1995. Finally, we are grateful to MITI, NEDO, and all of cooperative members of universities of industries. And also thanks to Professor Fleischmann and Professor Pons, Dr. McBride and his co-workers, and Dr. Kunimatsu for supply their electricity system to NHU laboratory, and their continuous support and cooperation. Thank you. And additional pictures attached in the poster. Please refer. Thank you very much.
Thank you very much. You have a very detailed description of the NHC project. So, are there any comments or questions?
Dr. Casavella, one of your overheads speaks of loading single crystallized ED. I have a language difficulty. You mean single crystal or once crystallized?
I made single crystal from polycrystal rod to study fundamental phenomena of the value.
When you add, however, the deuterium to it, and you get an expand, you get a volume increase, you maintain a single crystal.
Yeah, no. After the electrolysis, the single crystal is blocked and to the polycrystals, and many striation of the special striation is observed. And
once you start loading, then you get polycrystalline blade. Once you start loading with deuterium, you no longer have a single crystal, do you?
Yeah, I think so.
You think you do?
Yes.
No. 前回した始めたらもうシリングしたらないさっき
maybe at some loading ratio, the single crystal is destroyed. Maybe.
Your program is very commendable. If you were a small U.S. university, of course the U.S. has no such plan, would it be possible to apply to this program to get funding at the U.S. university? And who should we apply to? Who should we apply to? I guess we should talk to you privately later.
Yeah, I was curious about, you gave your budget from committee and so forth. I was curious about matching funds and how industry has been contributing. Industry and universities, have they been contributing in kind, or, I mean, in terms of money? You mentioned you got $30 million the first year, $5 million. What is the rest of the universities and industry been doing? Or have it?
Well, I think that will be that part of the story will be covered by the next talk.
Yeah, I think so.
Next one question about reproducibility. I'd like to know, for the most successful configuration of your cell, how many times did you fail in getting excess power, and how many times did you succeed in getting excess power?
In IMRA Japan type electrolysis cell, 2 times in pure palladium electrolysis.
How
Yes.
many experiments in the most effective
And
cell?
about reproducibility is about 15% or 20.
Thank you very much. So we go ahead to the next talk by Mr. Kamoto from the present status and the scope of the Japan Basic Research Project of New Hydrogen Energy.
Thank you, Mr. Chairman. I would like to introduce our basic research project of the new hydrogen energy. Just reply to the questions. And this project have been started in just the same, not today, but same season of the new national project. It means November 1993 or so. And so this basic means we or a cold fusion community should be complete the scientific basis for getting some confidence from the science or technology society, basing on the modern physics or chemistry or material science. Don't beyond in such a from such a common sense, because they know common sense only. So if we have some challenges to create a new field of deuterium material system to receive some very efficient energy or other products. So this basic research is very important to support the MITI's national program as mentioned by Dr. Asami now. So our object of the basic research is just written in this view graph. So the scientific basis for new hydrogen energy project, it means the national project, and this basic research project was supported financially by the 20 industries of Japan. And the budget, just this account. And last year will be 1996. I want to get the same budget from the industry, so I put some question mark in 1996. And this budget is only for researchers. So we have a little bit more budget to conduct or manage these basic researches through the IAE by Mr. Matsui, is a very famous gentleman in this community. So, and the organization is shown in something like this. So we have big sponsors from 20 industries, and they have promoting committees. And the budget is given to university through IAE, and we university has a conducting committee, consists of 9 members, and 9 universities and 11 or 12 research groups are involved this basic research project. And promoting committee, we have Mr. Honda from Toshiba Limited. He was a former chairman. And I chair these conducting committees. And these conducting committees gives academic consultant to the universities research groups. Oh, sorry. Kaput. How to? Okay.
In the middle.
Ah, I see. And the universities are just distribute all over the Japanese islands. It's very small islands, but very strong country. As you know, the strongest currencies we have, but we are not so rich. We are so poor. We have 4 research groups. First one is just calorimetry with sufficient sensitivity and preciseness and availability. And the second, it's mainly proceed by electrochemical researchers. And the second is correlation between excess heat and nuclear effects. One of this Professor Takahashi group, and the details was already presented in this morning. And the third is a very basic and a very fundamental research group. This group to clarify to find the possibility of nuclear reactions in ambient temperature or condensed materials. This was carried out. This has been carried out. Nuclear physics, and the fourth for the materials. And I want to show you some present typical result from the 4 groups. For the first calorimetry team, established very good calorimetric system with 3% errors and uncertainties, and availability for temperatures from 5 degrees C to 60 degrees C. And the second team have output as presentation by Professor Takahashi, and from us some very interesting correlation between neutron emission and excess heat. We are very high reproducibility for the excess heat generation, very appreciable, but not so big. And for third, some details will be presented by Professor Kasagi tomorrow, day after tomorrow. It's very, very good information or important information he gave us for multi-body nuclear fusion reactions possibility. And fourth, from the material science, we found new proton conductors may be it's available to realize the anomalous high D over PD loading ratio in the surface of this some kind of the perovskite materials. And also we have very important and very strong groups to establish the hydrogen material thermodynamics, especially to know the dynamic behavior in the deuterium or hydrogen isotopes in the palladium or other metals. And we have some scopes in coming 2 years. I mean, from this year to the next year, we want to provide more precise and more available calorimetric system, and we clarify the correlation between the nuclear effect and excess heat using multiple correlations. I mean the neutron, X-ray, or particles, and others. And also from the third group, we want to complete the basic nuclear physical knowledge. And also from fourth group, we provide a precise and accurate sensor system for the D over PD ratio or other information on the deuterium behavior in palladium. This is the last view graph of me. So the scopes second, I mean the end of the fiscal year of 1996, I hope, based on our basic research, to find some new hydrogen energy demonstration system by a national project at Sapporo Laboratory. Thank you.
Are there any questions or comments?
Two questions. First of all, I noticed on the slide you did talk about an inverse relation between neutron emission and excess heat. So do you yourself believe that there is an inverse relation from what you've seen?
Yeah, I have measured the neutron emission in terms of correlation with the excess heat.
That's what we've seen at Cal Poly. You've seen that.
Yeah.
The other question is, I didn't notice tritium studies on there. It seems to me
Tritium?
that's very important.
Tritium?
Tritium?
Okay. Only this, I missed the keyword of tritium in my view graph. Yes, every time we check the tritium concentration, of course.
Okay.
Yes, please.
Next question. In this case, how good is the reproducibility of your results? Because at the last speech was saying about two positive results. Now you're telling us that there are very good results.
In this 1 year or so, we introduced some pre-treatment of the palladium surface by maybe some introduction is given by Makuba. Our reproducibility is become better and better. So today, I can say we can get excess heat from heavy water system, but nothing from light water. And the reproducibility may be more than 60 or 70% in our group, not in the average number in Japan.
I have very high possibility.
I think there is a more positive note about Professor Kasagi's experiment. According to him, it is 100% reproducible.
Yeah. And Professor Kasagi want to reduce their particle energy to below the 10 keV or so. So we have very good access. Thank you.
Are there any more questions? We have still a few more.
No.
One question. In your schema there, I didn't see any experiment planned outside of the electrolysis experiments. Are you doing experiments on sonoluminescence and so on?
Maybe you have not such activities. But I talk only some brief introduction, and some details will be presented in the poster session or oral session.
Any questions? Yes.
What is the demonstration project?
This project should be replied by Dr. Asagi. Not from me, maybe. I mean, this is the target of the national project, according to my knowledge. So, my imagination, we set up some little but clear demonstration reactor.
Attention, Martin Fleischman's very nice, Martin Fleischman and Stanley Pons' very nice poster, which is right back there. It gets into a number of interesting issues associated with, among other things, apparent excess heat and such things as the Harwell experiment, one of the very, very condemning experiments of cold fusion. And just the basic philosophical question of when an experimental result is either confirmed or found to be not confirmed. So there are lots of interesting issues associated with this. And this particular session is dealing with this issue. It is entitled The Experimenter's Regress, and there are 4 speakers, beginning with Melvin Eisner, and then we will have Wolford Hansen, Melvin Miles, and Martin Fleischman. And we'll begin with Melvin Eisner.
What do you do?
I just stand there.
That's an unfair question.
So I'll bug you 5 minutes to go.
Well, let's see if we can get this thing working.
You have until 4:20. So I'll bug you at 4:15.
What I want to talk about today is some experiments, early experiments which were done in 1989, and I don't think that the results by themselves would be startling to anybody here today, but I'd like to bring out more or less the direction and the background to how these experiments were started and some of the ideas that were involved. But first of all, at the time of the Fleischman-Pons announcement, we were working on experiments on measuring the gradient of the gravitational field. Now, this is of interest in geophysics, exploration for gas and oil, for example. One can tell the difference between a reservoir filled with gas or a reservoir filled with oil. The notion is that what one is really interested in is measuring the gradient of the gravitational field. Normally what one measures is the gravity field over various stations, difference apart, and calculate the gradient. But of course there's always the problem of drift and stability. So the idea here was to get the gradient directly measured in one measurement. Just as a matter of interest, the patent office decided that this couldn't be done. They rejected the patent in the first go-around because it said it couldn't be done. Well, all of us who've studied elementary field theory know that if you want to measure a gradient field, you take a dipole, and the force experienced by a dipole in a gradient field is there's net force experienced by a dipole in a gradient field. So the only trick is to get a gravitational dipole, that is a negative mass. Of course, negative masses are easy. They're buoyant forces, and so our design was a buoyant force, a sonde, a little Cartesian diver with a positive mass and the buoyant force being balanced to a high degree of accuracy. One of the problems with measuring the gravitational gradient is that the Earth is spherical, and so there always is a gradient, which is essentially 2 over r, in other words, and the radius of the Earth, as I find out, is 2 pi times megameters, and I think that's how meter was defined, but I'm not quite sure why the 2 pi is in there. At any rate, the free air gradient for a typical, one of the constraints on this experiment was that the device must go down a borehole some 6 inches or 10 centimeters in diameter, so it had to be relatively small. And of course, typically 100 gram for the mass of the object, and separation between the positive and negative mass is about 5 centimeters would constitute a reasonable dipole. And on such a dipole, just the free air gradient, in other words, the surface of the Earth, there'd be about 2 micrograms force on such an object. In order to make the experiment useful for doing experimental work in geophysical interest, one needs to measure at least down to 20 nanograms. As a matter of accuracy, one can see then that one is trying to measure the mass of a 100-gram object, more or less, in parts in 10 nanograms, which is a pretty good experimental accuracy. All right, the whole trick of the experiment, what brings it into the cold fusion game here again, is that, of course, buoyancy is dependent on 2 factors: the volume of the sonde and also the density of the suspending fluid. Since the density is a function of temperature and the volumes are a function of temperature, one has to have a very accurate temperature-controlled environment. You couldn't do it except for the fact that water has a maximum of density of 4 degrees. So by working close to the maximum density point of water and taking into account the low expansion of quartz, making a quartz enclosure with a kind of bottom keel weight and top volume buoyancy, one can make a sonde, and essentially working around this point, one can see that there is about a 5 nanogram change in temperature, in weight, in buoyancy, per millidegree centigrade. Well, that puts fairly good constraints on the temperature control mechanism, but one more point, we're very sensitive to gradients in temperature, so that we must have a uniform temperature enclosure as well as having a constant temperature. All right, we were working on that project when the news of the Pons-Fleischmann effect came out, and we easily saw that this would provide us with a calorimeter. Our device would provide an excellent calorimeter for measuring the possible thermal effects. This gradient gravitometer was of interest to oil companies, and so you can understand energy was of interest to oil companies, and therefore we concentrated on the energy part, the heat production part. Just as a matter, here's a picture of the sonde, the bottom weight, lead weight, and a little shutter device here, fiber optic kind of device, very, very low power into the device itself to measure the displacement. And in order to actually control the force, to get a calibration force, there's a very small magnet here. We have a gradient magnetic field, again, a dipole magnet, to put known forces in on this. This is the device. All right, so it was relatively easy for us to just put a electrolytic cell inside that device, except whereas in our original calorimeter, we very carefully avoided having any energy sources inside and try to maintain the temperature as an isolated, if we got the outside of the calorimeter completely uniform temperature and the inside more or less same inside temperature, we thought we'd have a uniform temperature. The calorimeter essentially consisted of the container itself, an aluminum container with a heavy base, and this base was in contact with the thermoelectric element, and a quartz thermometer measured the temperature of the base, and the calorimeter, the dewar was surrounded by a water jacket circulated with thermally controlled water temperature, and then the whole device was insulated beyond that. So we could take this enclosure over here, and of course we needed to put power into the calorimeter in order to do the electrolytic cell. But what we were doing then was just to keep the heat flow. In other words, we kept the difference between the inside and outside temperature constant. The heat flow would be constant, so we could measure Q, or keep Q, the heat flow from the calorimeter, from the container containing the electrolytic cell to the outside world constant, and just measure the power required to do this. And therefore, if we have an isolated black box with heat coming in, going out, and power coming in, we could measure the power balance, energy balance, and all that. This was the thermal control system which was available to us, and it was relatively easy to use to adapt our control system so that we could control a given amount of power to maintain the temperature difference. All right. One other thing, that in order to balance, you have to balance the mass of the positive mass and the buoyant mass to get rid of to get a pure dipole. You have to do that with quite a bit of accuracy. Well, of course, when you start talking about nanograms, you really can't machine away a nanogram of material. And so what we adapted was to dilute the suspending bath, the water, with deuterium oxide, because that has a slightly different density, and so we could adjust the density by varying the concentration of deuterium in the system. Just as a matter of curiosity, although water has a maximum density at 4 degrees centigrade, the maximum of deuterium, D2O, is around 10 degrees centigrade. And, but there's a slight effect then in changing the D2O. But we had plenty of deuterium around, so that was helpful for our experiment. All right, our first experiment, what we did was, as I said, have a black box, maintain a constant temperature difference between the inside and outside, allow the heat flow to be constant. We had the power going in for the cell and a calibration resistor inside the aluminum enclosure, so that the sum of those two would remain constant. In other words, the power plus the cell current power equal the heat flow out would be the balance equation. All right, and as we generated or absorbed power in the cell, we varied P to keep the temperature constant and maintained basically a temperature difference between the inside and outside of about 14 degrees centigrade. To work with platinum, actually we went down and bought a little bar of platinum, numismatic 1 ounce grade of platinum, certainly not the best geometry, and its provenance or past history is unknown. It had some fancy numbers. You could put it in your safety deposit box. And, but that's what we used, and we just mounted that inside of a small glass enclosure. We plated platinum throughout the inside of the glass enclosure and had an electrode going through the glass to contact the platinum, and spot welded a platinum lead to the bar over here and covered the whole thing with the lithium OD solution that we made. And we ran this thing for 2 months. And we didn't know how long it was going to take, but primarily because we thought we had a very massive piece of palladium. We weren't surprised that energy just didn't pour out of the thing in a week or something like that. As a matter of fact, it took about 5 weeks before we saw net positive gain in energy. In other words, the power of the resistor went down in order to balance the heat flow, and so we were getting some positive energy out. And over a period of 2 months, we calculated that we got a 30% gain in energy. We terminated the experiment because we weren't quite sure about the calibration, and basically, although we had intended that we would get recombination on the platinum here, the platinum plating was insufficient and we were losing electrolyte. The cell had provision for venting, so we terminated the experiment at that point. That was the preliminary experiment, but the results were interesting enough to go to the next round. And say the first experiment started in April of '89, went for 2 months, and there was a gain of 30%. And as I said, the platinum recombination was insufficient and we lost electrolyte. So our calculations we thought might be a little bit chancy on that. So we repeated it again now we put in an improved recombiner and a lot of finely divided platinum in a fiberglass matrix and so on. And repeated the experiment for essentially the same geometry. And this one's get us a gain about 30%, seemed to work pretty well. But the platinum, the recombining electrode failed, and we had a problem with that. So we had to terminate the experiment. Again, we did the thing with a bigger recombiner and redesigned the cell a bit. And in August '89, ran another set. And again, we got here just a 10% gain, but we had some questions about the calibration, new size of the cell, etc. So we went to basically the experiment that I'm going to describe in some detail now, which is the end of the first careful bunch of experiments. But all these experiments were done with the same palladium ingot, probably a very bad choice in every way. Then we redesigned the experiment pretty much, and the calorimeter was designed rather specifically for this experiment rather than being the old calorimeter. But the principle is pretty much the same. We have the inside aluminum chamber in which the cell resided, and then some brass pieces coming out here which connected to the plate, which was the principal heat flow was through that region over there. There's a water jacket flowing around here, plenty of thermistors checking the temperature and insulation around the system, and pretty much work the same way. We believe that the measurements, the calorimeter is accurate to a fraction of a milliwatt. In other words, we can measure changes in that power with pretty good accuracy. It's all hooked to computers and things like that and recorded automatically. The cell itself was slightly redesigned. Instead of using the plating of the platinum, we had the platinum mesh. And now we used a different piece of palladium. This was an ingot of palladium, a rod, essentially, from which we cut something like a thick quarter, machined the edges, except the cast rough edge over there was left as cast. And here's the recombining electrode over here. And this vents the excess oxygen to a bubbler, to a mass spectrometer, which allows us to kind of figure out how much deuterium is going into the palladium there. But the design, this is just the electrolytic cell by itself. So just some numbers on it. The calorimeter, well, it required 2.486 plus or minus 1 milliwatt in order to maintain the temperature difference without any electrolytic cell action going on, to maintain a 10-degree difference between the aluminum can which contained the electrolytic cell and the outside world, which was the thermostatically controlled water. And the palladium itself was obtained from Atlantic metals, and it was 37 millimeters in diameter, 13 millimeters thick, and it was machined, the cylinder, the thick quarter was machined on its round over here, there, and the bottom was left more or less as cast. It was cast to make fine grain, quenched, heated up, and then quenched. We did an analysis, and the carbon content was less than 30 parts per million, platinum was less than 100 parts per million, and other metals, gold and so on, were looked for with equally small results. The electrolyte was made by combining 22 grams of lithium with 1 liter of D2O, and that gave us about a 3 molar lithium OD solution, probably more concentrated than it should have been or could have been. And so then we started. Now, here is an overall view of the experiment. Now I'll go back and look at some details on that. But first, we just started with a calibration time over here. The experiment started essentially October 24th, 1989, and you're on through essentially 12/18/89. Initially, there's a calibration port over here in which we just determine how stable the calibration is, no electrolytic current at all. Then we turn the electrolytic cell on, and we can see a charging energy over here. The dotted line indicates the current. The initial current was 100 milliamperes, then we went up to 500 milliamperes, back down to 300 milliamperes, again to 400 milliamperes, then down here to 40 milliamperes, and finally down here to 0 milliamperes. This is the energy, this line over here. Here, energy was being deposited in the cell, and then less energy was needed, and we kept gaining energy here over this period over there. Why we switched the currents, I guess we can see that this looked like it was saturating over here, stopping charge. We thought we wanted better charging, so we increased the current over there. It seemed to saturate again. We thought, well, if it seems to be saturating that, let's go back to smaller current, and we did. And then it's a little difficult to say what we did, why we did it, but to resist changing everything every minute was fairly difficult. This curve is basically the same as the other curve, except that it shows the net power. This line over here gives us the thermal loss rate, the 2 watts line over there. But when we take the difference, that is the power going into the resistor plus the electrical power fed into the cell, that's this squiggly line over here. All these transients largely are switching transients from changing the currents. And we can see that basically before the current is turned on, it's pretty level like that. But then, for example, here we see that there was some kind of transient which led to an increase in power. Here's another transient where there's another increase in power, and so on. When we decrease the current over here, there is a increase in power, net power, a little hard to see over there. These fluctuations, really don't know what caused them, but I guess listening to some of the talks today, I guess might have some clues as to what they were, but at that time we really didn't know too much about it. More detail on this is the turn on. So just the first day, say starting from 9 o'clock till 9 o'clock at night. So this is the transient. We're just getting everything up to the 10-degree temperature inside the cell. And you can see the time constant it takes to kind of thermalize the cell. But then these could be probably associated with maybe switching off the air conditioning in the lab or something like that. We really don't know what these are about. maybe again this is turning on some heat and something in the lab in the morning. Those are just control signals like that. But overall, it's a pretty good calibration line over there. And at this point, the current was increased, and that's more or less to get us the calibration line. In other words, this was our calibration line. This is the region where we turn the current down. In other words, the current had been at, let's see, what was it? 300, and then it went down to 40. And we switched it down here, and we get the switching transit. But then for a fairly long period of time, we get a strong power production, this part over here, and it really doesn't ever come back to the same baseline. Here you can see we're slightly above the baseline, maybe, and here we're slightly below the baseline. So this really indicated the start of a power turn-on. Now, subsequent to that time, we saw these transients. Here is one transient, and you can see the power is going along at this level. Nothing was changed, the current wasn't changed or anything like that. We saw this transient look very much like a current switching transient, but the current was being maintained constant by the power supply. And then we see that we've increased the power from here to here. In other words, we have an increase. This is, I think, around 40 milliwatts. This is around 90 milliwatts. This is 90 milliwatts, and that's, yes, this is 40 milliwatts, and that's 90 milliwatts. Again, we're followed by another transient later on, and this one maybe in the reverse direction. In other words, without any intervention, the current, the power essentially went from here to here after this transient. And again, no particular reason for it, at least that we know. We didn't change any of the operating parameters. Then finally, we turned off the current. And the reason we turned it off, terminated the experiment actually, we were still getting power out of it, but we were a little bit suspicious about whether the calibration could have drifted. And so we wanted to check the calibration. We thought that we'd established more or less the same kind of results we'd got before. All these experiments were really done under quite modest power conditions, and so we're really not trying to get huge amounts of energy out. We were trying just to make fairly accurate measurements. But we can see that when the tower is turned off at the end of the experiment, finally we get down to here. The calibration is pretty close. There is perhaps a small drift. The average here may be a little bit different than the average at the beginning, but it differs by, if we took that whole difference over the whole length of the experiment, it wouldn't still produce a significant result, difference in result. Okay, so what is the experimental major results? Well, if we take the energy, net energy put out, the integral of the energy or power curve, it's 50 kilojoules. After the experiment was concluded, we actually, before the experiment was done, we took a sample of the electrolyte and measured the tritium, and tritium content was 2.5 plus or minus 1 picocuries per milliliter. After the experiment was done, the electrolyte was measured again, and we measured 7.4 plus or minus 1.1 picocuries per milliliter. These analyses were done outside by another laboratory, but I believe them to be reasonable. We concluded that there was a significant change in the tritium content, but not enough to account for the energy, of course. the electrolyte volume, the recombiner worked well. We had 80 milliliters of electrolyte, and before and after, very much the same. We did chemical analysis on the surface and the content of the lithium, for example, and the lithium content was pretty much the same as, we didn't measure it, that is, we just combined 22 milligrams of lithium and put it with a liter of water, whereas the final result, we did some chemical analysis to find the concentration of lithium, but we seem reasonably close. We did X-ray fluorescence on the surfaces, looking for palladium, platinum, etc. And we could not locate any chemical constituents which would have been the results of chemical reactions, no molar amounts to account for the 50 kilojoules of energy. So that's pretty much the nature of the experiment. I guess there were subsequent experiments which I guess are not at a stage yet where we really want to, I would say they're best described as being incomplete, some fairly interesting things but not reproducible. The interesting thing is that the first 3 experiments done with the crudest kind of palladium ingot and so on seemed to work all the time. When we got more sophisticated, some of the subsequent experiments seemed not to work all the time. Again, we had to more or less resist the effort by the sponsors to expand the program to measure dimensions in the initial phases, although there wasn't any, we felt we had control and we're not under any great pressure to, well, mostly, although this is very old material, it really hasn't been published anyplace. And I thought it might be of interest just to say that at this early stage, based on rather fragmentary information, just using the equipment that we had on hand, in a sense, we were able to maintain, obtain what we considered significant positive results. I might say some other people I knew had worked the thing did not get positive results. Some of them I know used lithium hydroxide rather than lithium OD because they didn't think it made that much difference, that small amount of hydrogen and so on. So, and I don't think any of them ran for as long as we ran, and I don't think any of them had the precision of the calorimetry that we had used over here. Okay, well, thank you very much.
That was very good. I think I see why you fit into the theme. I really admire the fact that you kept going when there was so much negative going on. It was really quite admirable.
We didn't read the papers too much.
We do have time for one quick question. We started a little late, but yeah.
This parity issue is a very important one, and I think getting back to a talk earlier by Oleg, it shouldn't be assumed based on his talk that the Liebert-Liao thing was a bad experiment. I mean, that may very well have worked out, but later they had an impurity that was bad that is preventing their work. Impurities are going to be very important in all this work.
Well, I think also that goes along with the interesting theme of when you know a result is really valid and when you don't. And it's really a very,
a lot
very,
of failures were due to people rushing out and getting the highest purity.
Absolutely. And I noted in particular, you've got your first excess heat after 5 weeks?
Yeah.
By then, most people would have thought the whole thing was doomed. All right, well, let's move on. Wilfred Hansen is going to talk now. The title of his talk is A Statistical Approach to Electrochemical Calorimetric Analysis.
Yes, it's a real pleasure to be here. You know, excess heat is the signature of the Fleischmann-Pons effect, and its implications are just as profound now as they used to be. I want to tell you a little something this afternoon, simply, in fact, to tell you about our efforts to try to get as much information out of a, say, Dewar type calorimetric data as possible. How I got into this thing is historical, and just say this, that I've looked at I've looked at some of the Pons-Fleischmann data. I've looked at almost all of the Harwell data, and I've even done experiments with a Harwell cell that came from Harwell. Obviously, in the little time I have, I'm not going to tell you all about that, but I'll tell you a few things about what our results are. The next step up is that we have some real live cells of our own now based on the Pons-Fleischmann silver cell design. So let me quickly take you through a little exercise here. Here's a picture from an article by Harlow Group, and this is their cell over here. If you're like me, you didn't tell exactly what they had in mind there. The cell comes up like this, the glass comes on up, you see, and ends up there. There's actually a cork in there and a stopper in there, indicated over here. But here, this thing comes up and goes up like that, over there, and up like that. And in reality, this is a big blob of glass here, which is directly in contact with both the liquid here and the bath. In any case, looking back on it with experience we've had now, I think this is kind of a poor design because the liquid level is right here, and you can see as it goes down, the coupling with the conduction to the bath changes, and so it has a rather large tidal effect, as we call it, as this is an open cell and the material gets away. But nevertheless, with care you can get pretty good results from this. I'll say a little more about that later. Now, if I can keep track of where I put these, this is from Fleischmann and Pons paper, and I simply want to quickly show the improved variety is this one down here, which has silvering to precisely, well, one of the main points is to get rid of just what I talked about. The liquid level's up in here, and so now when it goes up and down, it doesn't have so much effect with regard to, for example, the radiation transfer of heat down here because of the Dewar, it's a Dewar up here, silver Dewar. It does change a little bit the heat out the top, but that's very small. It turns out to be about 10% or a little less than of the heat transfer, and so it doesn't matter quite as much as if it were the whole thing. Well, then the next group, which I want to briefly mention, is just based on this. But we've done I have some suggested improvements, some of which we've implemented in our own cells. For example, this wire that goes up like this should probably be eliminated to avoid, possibilities of recombination, although I've never seen that. Anyway, take this down here somewhere, pretend that. Now, the other thing is to take this KLF thing out of the bottom so that the bottom part has a radiation interaction with the bath that's similar to the rest of the radiation content. You see, this is a Dewar that's evacuated, of course. And then we put an insulating cork here, and in fact suggest that this be a little longer. So there's a little longer path here, but then you've got to be careful not to make it too long. So anyway, with some improvements such as that, and careful of how big a wires you put through it and so forth, we have essentially what we use, or are using now, as our own cells. So those are the three I have in mind. So first thing you have to do is model these cells. This model is pretty general, and I'm surely not going to go in great detail. Let me just say it's a power balance with some thermodynamics thrown in, and here you see the total input energy is divided up as follows. The voltage times the current. Now I don't subtract at this point that 1.527 whatever, plus any other heat source that might be there. In fact, QF is any other heat source that's on this side. Okay? Am I blocking myself? Sorry. On the other hand, this on the top side here, on the other side here, we have the electrolysis power, which is the power required to break up the molecule, and the radiation power. And we use both radiation power and and conduction power. Since this cell does have both radiation and conduction, we try to simulate that as close as possible, but it can be somewhat arbitrary. The conduction out the top is indeed conduction, whereas the other is radiation. Then we have the heat capacity power, which is the power required to move this thing around in temperature. And then the power for evaporation. Now, the next thing you do is you look at this thermodynamically, and I won't go through the details here at all. It's just that you can use certain cycles to make this more convenient and make the mathematics easier without compromise. Now, let me give you some data which will show a few things. Selected just to illustrate things. One is for a given Pons Fleischmann cell, which is not designed for heat production in the sense that I think it has a platinum cathode. So I'm not talking about excess heat here. I'm talking about performance of the calorimeter and how well we can understand the data set. This now is a list of these powers we're talking about. This is the total power. It says there, but since I've changed my nomenclature and so forth, really, what I would like to call that is just the input power. That first one I showed you, I times speed of the cell. This is the radiation power as a function of time. This is the electrolysis power, and since this was always at a given amperage, it's constant all the way across. The case, that's of course why we can subtract it. The KC power is the conduction power, and here I've got a little higher than I usually make the split. This was done some time ago. Then notice that there's the heater power, which is also on the left. If you put in a calibration pulse, this whole set doesn't even have a calibration. It doesn't even have one calibration pulse. And this is the evaporation power. Now you'll notice that none of those powers, including the evaporation power, is negligible. And nothing is neglected in the linear regression analysis, which we use then to get the answer to these things. So simply because we have this variation here of temperature, when you add water, you can do a regression. Otherwise, you probably couldn't even do it. But you can get an answer for this cell. In fact, it works out very well. There is a point when you dump in the water where this thing doesn't model very well. And so sometimes, depending upon how they handle that, if it shows up as a bad outlier, you have to get rid of a couple of points. But that's standard practice too. Anyway, let me just show you some results for that particular one, because it has a couple of nice illustrative features on it. And that is simply this. Look at the upper one. And there's a couple of things I want to tell you about that. First of all, that's a okay, first of all, what we do is you take this whole data set and do a regression analysis and get a Q, the KC. I leave the KR constant at a fixed and reasonable value. And the M, so you have three things. You just solve for all three of them. And when you do that, then you can take that KC, and in fact, what you did, because you know KC isn't constant, it varies, it's an open cell, and it varies during the day, but you can just consider that whole thing as noise. And that's fine, so you get an average. And what happens is that you can take the K you get, and now you can calculate Q at every point, which gives you all kinds of data. First of all, you can look at the overall position and say, hey, do I have an average excess heat? Or you can sum it up. Or you can once you got it in the computer, of course, you can do all kinds of things. Anyway, the point is, you've got that, and this linear upswing like that, and down, and upswing like that, is of course an artifact. But it's no great big mystery. You know exactly where it comes from, and what the significance of it being linear is, and the significance of it changing, and the significance of one being higher than the other, and so forth. Now, if you had an excess heat peak here somewhere, or one little short one, this would be an easy way to find out if you had excess heat as you went along, as opposed to, do you have an overall excess heat in the whole thing? Okay, so much for that. Now, let me show you another one. As I said, we looked at essentially all of the Harwell data, and there are so many interesting and significant things there. But here I want to introduce another concept. Many of the Harwell data were taken with no current at all at first. Actually, it was a very nice thing they did. I didn't see them make much use of it in their own analysis, but in my analysis it worked very well. For one thing, it showed me that their thermometers were off by a definite bias, and you could put that into you could do lots of things like that. But anyway, this is at a point before you've ever turned the current on. Surely we'll all agree that the excess energy should probably be zero. Now anyway, so now take this and do a regression analysis on it. Not only here, but you can do it at different places. But the concept I want to show is that you do it for this region. Actually, there's a couple more peaks over here. Now do that, and then just treat the Q of your heater as though it were an unknown. Don't tell your analysis that you know what it is. And calculate and see how close it comes out. Now, I put this up especially for those who say the cell isn't stirred enough. It isn't stirred at all, except convection. And you can do this with any region, as a matter of fact, from no stirring at all to stirring by a little amperage to stirring by a big amperage. And if you will take those regimes and individually do a regression analysis on them, you can get a beautiful analysis. All right, so that is the concept I wanted to tell you. Of course, you have to have some kind of calibration in there, but you will get a different calibration depending on what that area is. You sure you're giving me that you cut off at the beginning? Okay, well, I don't have very long to go. I will show you. I've got to show you a couple more things here, so we'll hurry. This is an example of the regressional analysis data. I still don't have dependencies printed in, a bunch of other stuff. So how can I go through this stuff and tell you what it means and so forth? Let me just say that from this analysis you can calculate an expected error. You do all kinds of things with your data, including the calculated expected error in the raw data itself, the calculated expected error in each one of these, and every one of them comes out and tells you what you can expect from different things. In this particular case right here, have I got that upside down or something? No, it's not.
Right. No, you got it right.
It's fine.
Well, but I'm trying to see it myself. Okay. Anyway, typical sigma for Q. This thing is Q, happens to be that. You can't see that on there very well. I need to look at the board, don't I? Okay, so on the second group down, on the left, the second one down is Q. First one down is the time. Second one down is Q calculated. The third one down is the calculated sigma you would expect for that. That is, if you carry out that same experiment n times, you'd expect to get that kind of a sigma. Anyway, there's lots of data on there. Now let me show you one of our own cells.
That's okay. Keep going.
And I want to show you what we got on that. Briefly, let me say that by making some improvements and being careful, we increase things about a factor of 4 better. Here, for example, we've tried to deliberately put this thing through the paces, and you can see that these are temperatures, and we don't wait for them to flatten off or anything. You don't have to do that. In this case, there's no current until you get out to here. Then you put a current in, and so forth. Well, do an analysis on this, and anyway, you can get all of your hours come out very nicely in a deal like that. You can identify each one of them, and the final result. Actually, you get a pretty good result if you take it all the way across, but it's better to take the two regimes. One where there's no stirring, and lo and behold, that gives us a sigma of about 5 milliwatts. And where you did have stirring, and all of those 5 different pulses at the other end, you get a consistency that's also about plus or minus 5 milliwatts. This little curve is due to the effective heat capacity. So, by using the different regimes, you actually get a different effective heat capacity, not very different, but different, and also a different K. But then, if you're careful about that, now, what's the implications? You take the Harwell data, they turned the current almost off and then did all their heat pulses to calibrate it for the whole thing. You see, you need to go back there and use each regime separately. For example, they quoted their accuracy at about plus or minus, well, 20% sigma. 15 or 20% sigma. And depending on which part of the paper you read. Now, the other part of that, though, is that what I'm saying is that we've taken that same data and we can get, depending on which part of it is, we can get an order of magnitude better accuracy than that, and almost everywhere a factor of 5 better than that. The unfortunate thing from the standpoint of first pass is that what we did was just prove that for all of those that we did that with, it was 0, even better than they said it was. So with that climactic conclusion.
You have a minute.
I still have a minute? Oh, gee, then maybe I can say what I was going to at the conclusion.
Sorry.
Aaron, you said 5 minutes. You said 5 minutes, and I thought that was it.
No?
Well, I'm just saying that, you know, with the ease of operation, with the cheapness of these calorimeters, and especially the fact that you can get different temperatures at will. You can use this thing clear up to. I was going to pose on you. You shouldn't have let me. Come on, I got one I want to show you. Yeah, right. What I didn't say when I went through this thing is, look, you have to be careful. Okay, this is assuming a pressure that, this is Pons Fleischmann cell done in Utah, so we're up in the mountains a bit. So you assume an appropriate pressure here, and look, it just comes across so beautifully. If you assume 1 atmosphere pressure, you get up to a point where it makes enough difference that it throws the whole thing off. Okay, so what I'm saying is that you can use this, as shown in here, you can use these things clear up to 90 degrees. Still analyze them just fine, and thank you.
My microphone is working.
Okay. I don't think we really have time for questions. I do have one question. I have been known to ask questions. What have the Harwell people said? Have you talked to them about your analysis?
No, I only talked to them through Mike Nealon.
What have the Harwell people say, Mike? All right, we'll talk about it. Okay, well, listen, Chief Concentration.
All right, 10 minutes.
My apologies, how many miles?
How do you put the microphone on? Where's the microphone? Right here. Okay, the title that I was given was Extraction of Information from an Integrating Open Calorimeter Over 6 Years of Fleischmann Pons Experiments. That was not my title, but I was given that title. I would have used a shorter title. But anyway, we started work in April of 1989 on this effect, the Fleischmann Pons effect. And we started off using various calorimetric designs, but basically, we had one type where the thermometer was inside the cell, and the second type where it is outside the cell. So in this case, it's an integrating calorimeter. The volume of liquid, if we used regular water out here, was about 60 cc's, where we had about 18 cc's inside. So it was not very sensitive to the liquid level. Where this is very sensitive to the liquid level and created a big problem for us. But this volume of water outside would integrate the heat effect. You can think of this as just a heating element if you want, supplying heat to this outer jacket. We know better ways to do that now. Rather than use water, you could use a metal block in here. That would be even better. We've got a new design where we do that. But anyway, then this is not sensitive to local temperature variations nearly as much as it is over here. So you don't have to worry as much about stirring, but I don't think stirring is a big factor anyway. But you don't have to be so concerned about inhomogeneities in temperature in this design right here. The reason we went to that design is that when we measured the temperature inside the cell, we saw a big effect as we lost solvent due to electrolysis. About a 3.5% decrease in K per gram. And unless you knew this pretty accurately, that was a big error source. And the other design did not have that problem. In our first studies in 1989, for 5 months, we ran various experiments, probably about 6 experiments using palladium cathode that we just had on hand there from a company out of business, Wesco, I believe. And we compared it with a platinum cathode, and you can see that they both give about the same effect, and basically no excess heat for either palladium or platinum. And so that was sort of one result that we reported and was published, that we had no excess heat. This, of course, was picked up by John Huizenga and his Energy Research Advisory Board, because I'm listed in that report in November 1989 as a group not reporting excess heat. So this is our result. Groups not observing excess heat, Miles Naval Weapons Center, and we're there with MIT and Caltech and Harwell with no excess heat. Apparently, I guess the critics think that we got much worse than calorimetry because later we got excess heat and they never believed that. But, but I hope that we got better, not worse, as time went on. The improvement we went to was using thermistors, which are much more accurate than thermometers. And we had 2 thermistors at 2 different levels. So this is a better design. We measure temperature at 2 different places on different sides of the cell at 2 different levels with 2 thermistors. Again, we have this large liquid volume, 60 cc's outside and about 18 cc's inside. So there's only a slight sensitivity to the liquid level in this design. And we've calibrated this many times, both by electrolysis, the power we put in, the delta T we get, temperature from inside the cell to the water bath, and we get a good correlation. Correlation coefficients are always 3 nines or better, and we've also calibrated by resistor resistor heating, joule heating, and we get similar results with that calibration. Eventually, we got a new source of palladium from Johnson Matthey in about September of 1989. We'd been using this older palladium up to that point and never saw excess heat, but with the Johnson Matthey material that was about 6.35 millimeters diameter, we did see excess heat for the first time after about 6 days. We got as high as 30% excess heat. This is the ratio of heat out to heat in. So we did get up to 30% excess heat. Less excess heat in the second cell. This is cell, what we call cell A. This is what we call cell B. They're always run side by side in series. But you can see there's less heat in this cell, much more heat in this cell. We had a power failure here, which is probably good that happened because it deloaded for a few hours, and then when we start up again, we're back to break even. So that shows that did go back to break even when the current was interrupted for a time period. But like most people, most of our experiments do not produce excess heat. I would say only about 1 experiment in 4 gives us excess heat. This is what it looks like in many experiments that we run. The heat out to heat ratio, heat out to heat in, if anything, we're a little bit below break even. This is break even right along here, and this is the net average. It's slightly below 1, and most of our experiments look like this. So our success rate is about 1 out of 4 experiments that produce excess heat. One argument that critics raise is there could be recombination. Now, we always check for recombination 2 ways. We measure the gas coming out of the cell at the time we measure the excess heat, and that always agrees with Faraday's law within 1%. And we also measure the volume of detail that we add each day. So we know how much detail we have to add to make up. So we have a double check to make sure there's not recombination. And we've never seen recombination with a palladium cathode that's fully submerged. But in 1992, we ran a different type of experiment where we used a copper cathode and palladium ions in solution, and we plate these out the copper. So this is a totally different type of experiment. It was a plating experiment. Stan Spock came up with this idea where you co-deposit palladium and deuterium at the same time. And when you do this, you get finely divided palladium, and that breaks loose and gets up to the top of the cell, and in some occasions we've had explosions because of the catalytic recombination. So we know we get recombination because the catalyst getting loose and floating to the top of the cell and coating the cell walls. But this shows you that we can detect that. This is the current efficiency that we measure by measuring the gases coming off. And you see it's always less than 100% in this type of experiment. This is the parent excess heat. And it looks like we had to have excess heat if you don't consider the recombination. But we know the recombination because we measure it. So if you correct for this recombination, it corrects back to here. And you can see we're back to break even. Heat in, heat out equals heat in. So when there is recombination, we detect it. And we can correct for it and get good results, as you see here. So recombination is not an issue. We can tell when we have it, and we can correct for it when we have it. But using a palladium cathode that's fully submerged, we never see recombination. Now, Steve Jones has recently made a big issue of this. You'll have a paper coming out, but he has no basis for his argument of recombination. This summarizes some of our early experiments. Starting off in 1989, using the old palladium we had on hand, we never got excess heat. When we got the new palladium, these are averages right here. The one experiment averaged 15% throughout the experiment. That was cell A. The other cell averaged lower. But we did get up to 30% for certain periods in that experiment. Then later we repeated this, got excess heat again, not as much. We ran H2O as a control, and that averaged out to break even. Then we ran a third experiment and got excess heat again. Then we didn't run any experiments for a period in here, and then towards the end of 1991, we wanted to test for helium. This is our first test of helium, and those experiments averaged excess heat, and we found helium-4 in the gases coming off. You may wonder why we didn't make much progress for a long time after that, and this is why. For almost a year, we never had excess heat again. You see all these experiments. There's a lot more than we show here. I don't want to keep putting dots up there, but roughly we ran experiments for a full year and never saw excess heat. And finally, towards the end of 1992, we found excess heat again. This is the average. We had some higher values there. And then we sent these samples off to Rockwell, and they tested out for helium that corresponded to the excess power that we measured. Then after that, we did co-deposition experiments through here, and again, we very rarely saw excess heat using the co-deposition, mainly because I don't think we had enough palladium. If you calculate the volume of palladium, it was very small that we were depositing, and I don't think our calorimetry was sensitive enough to measure excess heat. I think there may be excess heat in co-deposition, but we were not sensitive enough to measure it. If you integrate the power that we measured over the time, you can get the integrated energy. And our first experiment was 210 kilojoules, and the others were a little bit higher. Where we measured helium for the first time, that we ran that for several months, and that integrates to 1,400 kilojoules, or 1.4 megajoules of total energy. And that's when we did the first helium study. And this is our second helium study. This experiment did not show excess heat until after 6 weeks. It took a long time before it showed up. Then it only lasted about 2 weeks before it disappeared. So this gave excess heat, but not for a very long time period. And it took 6 weeks before it even showed up in this experiment right here. And then this is a more recent experiment, and the integrated energy right here. But I want to point out, if you assume we had palladium deuteride and completely burn that, you burn all the deuterium and all the palladium from the weight that we had, 4.3 grams of palladium, we would only get 6.2 kilojoules. So chemically, that would be the most heat that we could expect, the most energy. And you see we measured much higher than that, so it does not seem to me that you can explain it by a chemical reaction, even burning the palladium, oxidizing the palladium and oxidizing the deuterium in the palladium. I'll just go through this rather fast. This is our basic experimental procedures. We usually polish our palladium with silicon carbide paper dry. I'll just skip through this. I think the battery went dead on this. But anyway, we use a papyrus glass tube, a test tube, 1.1 molar lithium deuteride, LiOD, in our calorimetry. And we usually start off with low currents for 7 to 10 days to charge the palladium, and then we switch to higher currents. This is a protocol that we've been told to use. Then we usually run our cells around 40 to 60 degrees Celsius at 400 to 600 milliamps as a typical experiment. There's no steady state in the calorimetry. As you can see here, the cell voltages are always changing, the temperature is always changing. So this just points out that there's not a steady state. We add the D2O, and there's a big increase in the voltage, but the temperatures and voltages do change in a linear fashion, which helps us evaluate the calorimetry. We recently published a paper. I may have copies of this out of the poster after the session, which discusses the calorimetry. We don't have time to go through all these equations now, but these are basically the same equations originally proposed by Martin Fleischmann and Stan Pons. They're complicated equations. They're actually differential equations because there are derivatives in here, but this is the power in, and the power carried away by the gases coming off, and the change of the power in the calorimeter itself. But it'll take a while to go through all that. To evaluate this, you need to know the heat capacities as a function of whatever the temperature is. So these are the equations that we use for the heat capacity as a function of the temperature. And this shows how the gas term, the power carried away by the gases, how it can become important at higher temperatures. If you're working around 50 degrees, maybe you don't need to worry too much about the power carried away by the deuterium gas and the oxygen gas and the D2O vapor coming off. But as you go to higher temperatures, you have to be very concerned about it. It can become very large. And that's mainly because of the evaporation, the latent heat of evaporation of the D2O itself. So of all these terms, that last term involving the L is the largest term because that involves the evaporation of change of D2O from a liquid to a gas, and that becomes the major term in that equation. So you have to consider these full equations, especially if you're working at high temperatures, as you get up above 60 degrees. And in addition, you need to be concerned about, in our case, the heat carried away through the top of the cell to the room temperature. The room temperature does play a big effect. And our major improvement recently is we have a secondary box over the top of the cell to keep the temperature at the top of the cell more constant, because that's a big error. If the room temperature changes 1 degree, that can produce a big error in your results. This lists some of the error sources in the calorimetry. But as you see, the largest term here is the room temperature change. A 1 degree change in room temperature in our cell will produce a 1% error in the calorimeter. And that is about our error range today in our calorimetry of my design. We've got a newer design that's much better than that. I can measure to about plus or minus 20 milliwatts with this new design that his postdoc has developed. He's now getting accuracy of plus or minus 1 milliwatt. This is a summary by Ed Storms that just shows you that our results, when this was written in 1991, these open circles here fit in well with other results. If anything, we are a little bit low for the current end. This is dead one. Okay. Okay, the battery's dead on that other thing, but the main thing of this slide is what other people mentioned is this morning, Mike McCurby and others, that the plating material that we use is very important. The Johnson-Matthey, Fleischmann and Pons, and other Johnson-Matthey, the ones above there were all basically Johnson-Matthey materials, and you can see that we had 12 out of 15 experiments gave excess heat in that case. So there are some sources of plating that we get that we have a high success rate.